तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so last class we were discussing the different circuit variations in ECL, primarily aimed at reducing the power dissipation in ECL gates, which is a primary drawback of ECL gates. Okay, today's class we shall take up some technology related aspects, basically to improve the speed performance of ECL gates. We know that ECL is the fastest logic circuit, okay, and there is a lot of effort to improve the speed, okay, and make it as fast as possible, okay, to reduce the delays. And one way to do that is to have improved technology. Okay, so we shall take up some of these issues in today's class. Okay, now if you look at a bipolar transistor, bipolar junction transistor, we have drawn the circuit, we have drawn the cross section quite a number of times. Okay, you have this is the emitter base junction. Okay, this is the base contact, say. All right, so this is NP, this is the emitter base junction. Okay, and the delay in a circuit, as we have seen, is dependent to a large extent on the emitter base junction capacitance, okay, because the emitter base capacitance, which means of course the junction capacitance as well as the diffusion capacitance. Of course, in emitter base junction it is the diffusion capacitance which dominates, okay. That is because there is large charge storage, okay, and the diffusion capacitance is many times larger than the junction capacitance, okay. So that is the problem. So we have to see how we can reduce this emitter base junction capacitance, emitter base capacitance as such. Okay. One way to reduce the emitter base capacitance is to reduce the area. All right. So if you look from the top, okay, that is you have the emitter region like this maybe, and then you have the base, okay, and you have the emitter contact here and the base contact here. So if you reduce this area of the emitter region, okay, you will reduce the capacitance, okay. So we shall see how the emitter base area affects the base emitter capacitance, okay. Now this capacitance, when we talk of it, is actually we can break it up into two parts, okay. One is due to the charge stored in this region, okay, all right, this part of the junction, okay, all right, which is called the plane region of the junction, okay. And there is another part which is also important, which is the sides of this junction, okay, the sides here, all right. The sides we can call it the peripheral region, okay, and the plane, and this region is the plane region, okay. So you have a component of capacitance due to the plane region and you have a component of the capacitance due to the peripheral region. Now the area of the plane region is the area of the mask, okay, this is the emitter area, all right. Okay. And what is the area of the peripheral region? That is going to be the perimeter of this region into the junction depth, all right. So this is the area of these sides, all right. So you have charge storage not only here, okay, but also on the sides of this. Okay. So, the capacitance is partly due to the plane region, okay, and partly due to the peripheral region. Okay. I will just give you some data, okay, and I think from this data certain points will become very clear. Emitter size in microns, okay, emitter junction depth in micron, emitter base capacitance in femtofarad. This is the plane component and the peripheral component. Okay, some data I am just going to write here. So, emitter size in micron, okay. So, if you have a 1.5 into 1.5 emitter size, okay, and the emitter base junction depth is 0.2 micron, okay, the plane component is 4.1 femtofarad and the peripheral component is 3 femtofarad. Okay. If you reduce it to 0.1 micron, that is the junction depth, okay, this one remains 4.1 because we are not changing the emitter area. Okay. But this peripheral component reduces to 1.6. Okay. If you reduce the junction depth even further to 0.02 micron, okay, this one remains unchanged, whereas the peripheral part becomes 0.4 femtofarad. Okay. Is it clear? Because the junction depth reduces, the area of the peripheral part is basically reducing. Okay. Now, suppose we go for a 0.5 micron into 0.5 micron emitter size, okay, and again the junction depth is 0.2 micron. This one has gone down to 0.46 femtofarad. Of course, the area itself is reduced from here. Okay. The peripheral part is also less at 0.99 femtofarad. If you go to 0.1 junction depth, this remains the same, and the peripheral part is 0.55. 0.02, again 0.46 is the plane component and 0.14 is the peripheral component. Okay. Now, if you look at this table, what is the message it gives? If you compare, okay, this part, this set say, and this set, okay, you see that what we have done is the emitter size has been reduced. Okay, as we had said, in order to reduce the capacitance, we have to reduce the emitter size. Okay. So, emitter size has been reduced. Correspondingly, the plane part of the capacitance, okay, has reduced from 4.1 to 0.46. Okay. So, this has been reduced 1/3. So, the capacitance would be reduced by 1/9 area. Okay. 1/3 on each side. Okay. So, the capacitance is just proportional to area. Okay. But you see the peripheral component has not reduced but that much. Okay. So, in fact, the peripheral capacitance is much higher than the plane capacitance. Okay. All right. So, but if you go on reducing the junction depth, okay, then only say if you go for 0.02 micron junction depth, okay, that is the emitter junction depth, then only you find that the peripheral component becomes less than the plane component. Okay. All right. Because the, again just to reiterate, the plane component is proportional to a squared. If you say one of these sides is a, all right, and the peripheral component is proportional to a, because it is proportional to the perimeter into the junction depth. Okay. So, if you reduce A, that is one of the sides, if you call this A, all right, this is A, say one of the sides of the emitter is A. Okay. If you reduce A, the perimeter to the area ratio goes up, okay, and the peripheral component starts to dominate. So, what you have to do is, okay, when you go for smaller and smaller dimensions, okay, of the emitter, okay, in order to derive the benefit of a lower capacitance, you also have to reduce the junction depth. Otherwise, it makes no sense, because it is the peripheral part of the capacitance which is starting to dominate. You are just, by reducing the area, you are not getting enough benefit. Okay. Is that clear? So, now you have to reduce the junction depth, that is, this junction depth has to be reduced. Okay. Now, what happens if you reduce the junction depth, the emitter junction depth or the emitter width? Okay. Now, we have seen a relation for the beta of a transistor, okay, and we have also seen that the beta of a transistor is proportional to, among other things, the proportional to the ratio of the base width to the emitter width. I mean, it is the other way around. For higher beta, you require reduced base width. Okay. So, it is proportional to emitter width by base width. Okay. Beta is proportional to WE by WB, okay, where WE is the emitter width, all right, and WB is the base width, all right. So, if you reduce the emitter width in order to reduce the capacitance, the beta is going to get affected, all right. So, you cannot, again, from other consideration, you cannot reduce the emitter width. So, what is the solution? Well, the solution came in the form of a particular type of bipolar transistor, which is called the polyemitter bipolar transistor. Okay. Okay, I just going to discuss that. What is a polyemitter bipolar transistor? In a polyemitter bipolar transistor, the advantage is that you can reduce the emitter junction depth, okay, without affecting the beta of the transistor. That is the major advantage, okay. And all modern high frequency bipolar transistors are in fact polyemitter bipolar transistors, okay. So, what you do is, sometimes it is called PET, all right. Okay. Now, what you do is, you know that in a BJT, if this is the emitter region and this is the base region, if this is the minority carrier profile, all right, and this is the metal. So, this is the metal interface, okay. The minority carrier profile in the emitter region, okay, this the minority carrier concentration goes to 0 at the emitter, at the metal contact, okay, because here the recombination rate is very high, and so the excess minority carrier concentration goes to 0. Okay. Now, if you reduce the emitter junction depth, this is the emitter junction depth, the slope is going to go up. Okay. So, basically the injection of holes from the base to the emitter is going to increase, and that increases the base current, all right. So, what we are saying is that in fact for high beta, the emitter thickness must be larger, okay, to reduce the base current, but that gives rise to problems of the peripheral capacitance. So, what is done is, you have, if this is the silicon part, okay, you have another part which is polysilicon, okay. So, you have a silicon polysilicon interface, okay, and then you have the metal. Okay. If you have such an emitter structure, okay, this is the entire emitter is now consists of two parts, one is polysilicon and the other is silicon. The profile is something like this. You have, it is almost, here you have a small difference because there is some recombination at this interface, but the recombination is very small. So, in fact, the carrier concentration is going to go to 0 at the polysilicon metal interface. Okay. So, the profile is almost like this. So, the total emitter width for calculation of beta is actually the sum of the polysilicon thickness as well as the silicon thickness, all right. So, okay, which is can be made quite large, okay. Whereas, we shall see when we look at the transistor structure as such, the peripheral capacitance is going to be determined by the silicon thickness, okay, which can be made very, very small. In fact, it can be made as small as 0.01 micron, okay, which for all practical purposes is going to eliminate the peripheral component. Okay. So, you make the silicon part very small thickness, you make a very wide polysilicon thickness. Okay. So, the peripheral capacitance which depends on the silicon thickness is reduced, whereas the beta which depends on the emitter thickness, the larger the emitter thickness, the larger is going to be beta. Okay. So, you have a high beta. Okay. All right. So, in fact, in this polyemitter transistors you can get very large gains. Gains means current gains, that is beta, okay, because of this property, okay, of using polyemitter. And in fact, again, because you get a large, you can have a large WE by WB ratio, okay, again you can trade it off with the doping concentration ratio, okay, and in fact you can also increase the base doping concentration, which has other effects like reducing the base resistance and all, okay, which is advantageous from the circuit point of view, because the base time constant, okay, to charge the base would be reduced. Okay. So, these are the advantages, all right, of a polyemitter transistor. Okay. Now, we shall see how actually a polyemitter transistor can be fabricated, or what does it look like finally. Okay. So, that is the next thing we shall take up, because it is very important from, especially from the ECL point of view, because ECL, you know, is a high speed circuit, and almost all modern ECL transistors are in fact polyemitter transistors to derive the benefit of high speed. Okay. All right. So, I shall take up now the structure of the polyemitter transistor, okay, and how one can actually fabricate a polyemitter transistor. Okay. So, the steps. First, suppose you have, this is the P region, okay, which is the base of the transistor. Okay. All right. Now, we want to fabricate the polyemitter on top of this, PN junction, okay, the emitter junction on top of that. So, the first step is, grow silicon dioxide, okay, which is going to be which is grown thermally. Okay. You grow a silicon dioxide, okay, open a window in silicon dioxide. So, you open a window in silicon dioxide using a mask. Okay. So, what you do is you open a window in silicon dioxide, you have a structure like this. Okay. It is here where you are going to form the emitter base junction. Okay. All right. Then what you do is deposit polysilicon and dope with arsenic. Okay. Arsenic is a N-type dopant in silicon. Okay. It has the property that it has got a very small diffusion coefficient, that is, it does not penetrate much into silicon. So, if you want to form shallow junctions, okay, you have to use arsenic. With phosphorus you cannot form shallow junctions because it diffuses very fast into silicon and you cannot control, the control is not so good enough to form shallow junctions. Okay. So, arsenic is usually used for when you want to make shallow junctions. Okay. So, basically what you do is you deposit polysilicon on top of this. Okay. And this is doped with arsenic. Okay. That is, you introduce arsenic impurities here on the top. So, this is actually doped with arsenic. So, it is N type, okay, N type polysilicon, and it is very heavily doped. The doping concentrations are made very high. Okay. Now, the third next step is you pattern the poly again by lithography process. Okay. So, you are left with some of this. Okay. All right. So, you are left with this. Okay. Oxidize the polysilicon and drive in the arsenic. Okay. So, this is done simultaneously. Oxidation of polysilicon is a high temperature process. Okay. And as you oxidize the polysilicon, okay, what happens is the arsenic impurities in polysilicon, they also go into the silicon. Okay. They diffuse into the silicon. Okay. And so, what you have is you have another oxide layer on polysilicon, since you have oxidized it. And simultaneously you form an NP junction here. Okay. This PN junction is formed. This is the N type. Okay. I am sure you cannot see this, so I will write it. This is N type. Okay. All right. So, this is what you have after step 5. Again, then the next step, final step, open window in oxide for emitter contact. Okay. That is, you again open a window here in this oxide here, all right, and then you deposit metal. Okay. So, this is the emitter contact. All right. So, you see this is the emitter base junction structure here, polyemitter of a polyemitter transistor. Okay. So, for, as I said, for calculation of beta, okay, the total emitter thickness is going to be taken as this thickness inside the silicon of the N region. The N region is starts from the junction here right up to the metal contact here. Okay. So, the total emitter thickness WE is actually this. This is WE. All right. That is the total thickness, because the carrier concentration which has its the minority carrier concentration in the emitter, which has its peak here, is going to go to 0 at the polysilicon emitter contact, whereas the peripheral capacitance you see is due to this part here. Okay. All right, is due to this part of the junction here. Okay. So, this you see is very small. The part of the junction inside silicon is very small. So, the peripheral component of the capacitance is virtually eliminated. Okay. So, you have high speed transistor as well as a high beta. Okay. So, this is the emitter based structure of a polyemitter transistor. Okay. That is how you make a polyemitter transistor, and as I said that virtually all high speed transistors nowadays, okay, are silicon transistors, okay, are polyemitter transistors. Okay. All right. So, we shall go ahead. Now, okay. Now, we shall see with this now background knowledge, we shall now go ahead and see how to evaluate the delay in a ECL gate. Okay. All right. I just leave it here. In an ECL gate, I will just draw the ECL gate once more. You have a current source here, say. This is the input, this is the reference voltage, and this is the emitter follower. Say I am just taking the NOR output. So, these are the resistances. Okay. This is ground and this is minus VEE. So, this is actually RE, say emitter resistance, emitter follower resistance, we call it CL. This resistance we call it RL, okay, and of course, all right. So, you have this as RCS, this is the current source resistance, okay. All right. Now, the way we it is the delay is actually calculated in a ECL gate is like this, okay. The total delay is taken to be, okay, the total delay TD is taken to be the sum of the forward transit time of the transistor tau f, say, okay, plus a weighted sum of all the capacitances and resistances in the circuit. All right. So, that is the total delay, the sum of the forward transit time of the transistor plus a weighted sum of all the time constants in the circuit, all right, all RC time constants in the circuit. Okay. Now, what are the different capacitances and resistances in the circuit? Okay. Now, if you take up the resistances, okay, you have the external resistances. If you look at the circuit RL and RE, so these are the external resistances. Okay, in the circuit RL and RE, sorry. Okay, and then you have the internal resistances in the transistor. Okay, they are usually written as RBI, that is the base resistance, intrinsic base resistance. Okay, intrinsic base resistance. I will explain what it is. RBX is the extrinsic base resistance, okay. Then you have the emitter resistance, and the RC is the collector resistance. So, you have 6 different types of resistances in the circuit: intrinsic base resistance, extrinsic base resistance, emitter resistance, collector resistance. These are all internal to the transistor, okay. And then you have the external resistances RL and RE in the circuit, okay. Now, capacitances, which are the capacitances you have in the circuit, okay. you again have a number of capacitances in the circuit. Okay. I think to write here. Capacitances. Okay. You have CL, the load capacitance, which is the external capacitance. This, okay, which is the load capacitance, and then you have the internal capacitances. Okay, you have CJE, which is the junction capacitance of the emitter based junction. I'll write EB junction capacitance. Okay, CD, which is the EB diffusion capacitances. Okay, and then you have the CJC, this is the other junction. Okay, that is the collector based junction, CJCI, which is the intrinsic collector base junction capacitance. Okay. Then you have CJCX, which is the extrinsic collector base junction capacitance. All right. And then you have one more CJS, which is the collector to substrate junction capacitance. So again you have 6 capacitances. Okay. So in fact here you have 37 terms. Okay. So what people have actually done is evaluated the effect of all these capacitances, okay, and in fact developed weighting factors for all these capacitances, okay, in order to obtain the delays. Okay. Now just before we go ahead, what are these components? We'll just have a look when we by taking up the transistor structure as such. We'll go back to this transistor structure here. So this is the emitter based junction. Suppose you have the base region, you have the base region like this. Okay. Then you have the base contact somewhere here. All right. So you will have the base metal here. Okay. So this is the base contact. Okay. Now if you look at the values of the resistances, RL and RE are external resistances. Okay. Now you have RBI and RBX. RBI is the intrinsic base resistance, which is usually this part of the resistance, okay, that is intrinsic. So this is the intrinsic transistor region, okay, that is, this is the region where you have a transistor action, okay. So this part of the device is called the intrinsic region, all right. Okay, here you have the transistor action taking place, all right. So this is the intrinsic base resistance, and then you have an extrinsic base resistance, all right, that is from the contact right up to the intrinsic device region, okay, all right. Then you have emitter resistance. You also so here you will have, this is the P region for the base, you have the N region, okay, and then also you will have the substrate, okay, which is again a P. So this is the, you will have a collector resistance, okay, of course you will have a buried collector N plus here as in a PN as in a bipolar transistor, you know, but there is going to be a again a resistance, okay, from the collector, for the collector, okay, collector resistance from the intrinsic part of the device to the contact, okay, and also you have an emitter resistance also. So these are intrinsic internal to the device, okay. Capacitances, if you look at the capacitances, you are aware that one is the load capacitance, external capacitance, you have the emitter based junction, okay, you have the two types of capacitance, one is the junction capacitance and the other is the diffusion capacitance, okay, one is due to the depletion layer region, okay, and the other is due to the stored charge, okay, all right. Now CJCI and CJCX, Okay. CJCI is the capacitance for the intrinsic part of the junction. Okay. Again, this is CJCI will be the capacitance for this part, okay, of the device. This is this capacitance. Okay. And CJCX is basically the extrinsic capacitance. Okay. This is the extra region. You have a junction here. Okay. The junction goes all the way, all right, base collector junction. So, this is extrinsic. Okay. This is actually not taking part in the transistor operation. Okay. Transistor action takes place here, but you cannot avoid it, this region. Okay. So, you have all the capacitances there. You will have a junction. Okay. This is reverse bias junction, and so you will have charge here. Okay. So, that is the extrinsic capacitance, and again you have another capacitance from the collector to the substrate. Okay. So, these are all the capacitances. Okay. All right. So, one has to see how to reduce these capacitances, okay, or as well as the resistances, in order to improve the speed performance or to reduce the delay. Okay. Again, what is done is you have what is called a self-aligned structure. Okay. You must have a self-aligned structure to reduce these values, to reduce the values of the parasitic components, all right, all the parasitic components, that is, which are not actually taking part in transistor operation, for example, the extrinsic components, okay, but which has an effect on the performance. Okay. So, just to give you a small idea, I am not, there are many complicated self-aligned processes. I just going to show you a simple process, okay, something which is should not be much difficult to follow. Okay. So, basically, all right, you have the N region here. Okay. Then this is the oxide. Okay. What you can do is you diffuse the P region, which is the base region. All right, you diffuse the base region. Of course, this junction depths and all are shows a very big P diffusion, but these are not to scale anyway. So, then what you do is, once you have the P region, okay, you deposit polysilicon, okay, all over and oxidize it and etch back. Okay. It is something similar to what you have done in the I squared L process, if you recall. So, finally, what you have is you have N plus polysilicon here, say, okay, and you have oxide around it. Okay, this is polysilicon. All right, N plus polysilicon is deposited. Okay, you oxidize the polysilicon and you etch back. It will leave a oxide around it because of the fact that polysilicon oxidizes at a faster rate than silicon. So, all this you can etch out, in fact, on the oxide on the silicon. Okay, all the oxide on the silicon is going to be etched back, leaving behind oxide on the polysilicon. Okay. And then what you do is you again do a P diffusion, okay, and this diffusion is going into the extrinsic regions. Okay. So, you make these regions P plus. Okay. Why are you doing this? To reduce the extrinsic base resistances. Okay. So, this region, it becomes P plus. So, basically the structure becomes something like this. Okay. You have P plus regions, all right. And then what you do is you deposit, okay, sometimes you can deposit metal right away, or if you can also deposit P plus polysilicon, okay, to take contact from the base. Okay. So, you can have the metal going around like this. Okay. You have the metal going around, the base contact metal going around like this. Okay. All right. Now, if you look from the top, okay, this what does the structure look like? Okay, you have this is the base region. this is the base region. Okay, then you have the emitter region here, somewhere here. All right. Now the emitter poly, okay, actually it goes like this from the top. Okay, it is not, and you take the emitter contact somewhere here, say. All right. The emitter poly, which is shown here, it goes like this way. This is the top view, okay, and you take the emitter contact here. All right, and all this emitter poly is covered with oxide. So, okay, on top of that you have the base metal or polysilicon, okay, and that you can take a contact somewhere here, or even you can take it out you can take it out this way. This is the base metal, okay, you can even take it out and have a contact somewhere here, okay. All right, you understand? So you have the emitter metal running this way, the base metal running this way, and because of the oxide covering the emitter poly, okay, you have there is no connection. Of course, I just made once you do a drive-in, okay, one step I missed out. So this is the N plus poly. So once you do the drive-in, you have a PN junction in the silicon. Okay, so this is basically a polyemitter transistor. Okay, all right. So this is a polyemitter transistor. Okay. So this is a self-aligned transistor, and in a self-aligned transistor, the parasitic components will be very much reduced. Okay. So just to give you an idea of the values, see RBI, for example, this is conventional, this is self-aligned. Okay, it will be, say it is 125, this is for a particular process, okay, this is 125 ohms, okay. Then RBX, okay, this is say 257 ohms, this can be as low as 13 ohms. So this has been published for a particular process, I am just giving you the results, okay. The other interesting thing is CJCX, okay. So it is 17.9 femtofarad, this goes down to 4.5 femtofarad. Okay. So because the extrinsic part of the junction, okay, this junction here, if you look back at this circuit, there is a large extrinsic part for taking the base contact. Okay. Here, because of the self-aligned nature, okay, the emitter and the base are self-aligned, and the base contact is just separated from the emitter region by this thickness of the oxide here, which is just about maybe 0.4 or 0.3 microns. Okay. So you see that the extrinsic region has been cut down drastically. Okay. And so a high speed transistor, okay, must have a self-aligned structure, okay, so that the extrinsic regions are reduced, so extrinsic capacitances are reduced, okay, which gives rise to lower delays. Okay. So in fact, a self-aligned transistor is going to be much faster compared to a conventional transistor. Okay. All right. Now I shall just take up one more issue here. I shall also discuss the heterojunction bipolar transistor, but maybe before I go into that, I will just like to discuss something about the delays. See, we have always said in our discussion that we talked of I naught into R is equal to, say, we have said V on sometimes we said I naught into R is 500 millivolts, because I naught into R in a ECL gate, that is the current source value into the load resistance, okay, that is the logic swing, that is the amount by which the output voltage changes, okay. And we have never said, okay, how to choose I naught and R, okay. What is important is the drop across the collector resistance, okay. Now is there anything, okay, is there any way, or you can just choose any value of I naught and any value of R, okay. Now if you look into this expression here, okay, there are many components of the of delay, okay, many time constants in, okay, there is the tau f, and there are 36 other components in that summation sign, okay. Now out of that, the major components, as has been seen, is consists of RB, CJ, X, RB, CD, okay, RL, CJ, CX, okay, this is CJ, CX also, all right, RL, CL, okay, then of course RB, okay, RBCD is already there, then of course tau f. So these are some of the major components which give rise to delay, okay. There are other time constants, but their contribution is less, okay. Now if you look at these values, okay, you see that, what do you see? Suppose you have you are designing for a particular logic swing, okay, that is in the ECL gate, the I naught into R is say a particular value, okay. Suppose you say that I naught into R should be 0.4 volts, okay, that is the drop across the resistance when the full current is flowing in a branch is 0.4 volts, okay. Say that is I naught into R, say RL is a constant, okay. Now if I plot the delay versus I naught, that is basically what I want to say is, does the delay depend on the value of the current source, okay, that is what is the current which you are using, okay, all right, in the ECL gate. So if you look at these components, you will find that tau f is independent of I naught, okay. So it is going to be something like this, a constant, and then you have other components, say CD, okay. What does CD depend, is CD dependent on I naught? It is dependent on I naught, okay. So CD is proportional to I naught, all right. So all the components, okay, which have CD, okay, that is R, we should say CD to all R, okay, all the components, okay, CD, here is shown CD RB, that means basically RB X, RB intrinsic, and also the other components, okay, all these components, okay, will increase with I naught, okay. And then you have the other components RL, which has RL in them, okay. What is going to happen if you increase I naught, what happens to RL? I naught into RL is a constant, okay. So RL is going to reduce basically. So all the components corresponding to which have RL in them, they are going to reduce, okay. So you have like this, these components which have RL, okay, all the C's, okay, into all the C's, okay, all the capacitances, okay. So these components are going to reduce, all right. So what you get, the point is that if so you see that the total delay is going to be the sum of all these delays. So, the delay is going to be something like this, all right, which basically means what we want to say is that if you want to keep the logic swing constant, okay, that is I naught into RL constant, then there is a particular value of I naught which is going to give you a minimum delay, okay, all right. So, you have to bias the ECL gate for that particular I naught to get the minimum delay, and then you choose RL accordingly, so that I naught into RL is equal to the logic swing. So, if you are chosen 0.4 as your logic swing, you can have all sorts of combinations of I naught and RL to get 0.4 volts. Okay. Now, what you are going to choose as the value of I naught and what the value of RL. So, you have to see at which I naught the delay is minimum, okay, all right. So, depending on that you bias, you choose the value of I naught, and accordingly the value of RL is going to be fixed, okay. So, the point is the delay is not independent of I naught, but there is a minima, okay, and the ECL gate must be biased for that at that I naught to get the minimum delay, okay. So, we shall stop here today.